This is a video about water, and water is something that we call amphoteric, which I'm going to explain to you. And then also we can calculate the KQ, or the equilibrium constant for water, and when we do that we call it KW. So first thing is, and you saw this in the previous video, water is amphoteric. So what happens is amphoteric means it can be an acid or a base. And in the video, he was discussing how just two nearby water molecules can collide with one another and transfer a hydrogen. So you can see, for example, if we link these, this is water acting as a base because it accepts a proton, and then this one over here is acting as an acid. So water also, so it can do that when it's all by itself in pure water, but also when it's in mixed with an acid or a base, it can itself then act as an acid or a base. So this is two examples. One of these, the water is acting as an acid, and one it's acting as a base. So pause the video and try to figure that out. So if you link these, you can see this water was acting as a Bronsted-Lowry base because it accepted the proton from this hydrochloric acid. And then if you look at this water, it was acting as a Bronsted-Lowry acid because it donated a proton to the NH3. So that's just, another example. And also there's other things other than water that can act as acids or bases. So for example, this hydrogen sulfate ion can be a base. So if it's in water, and if it's acting as a base, it's going to accept a proton and become H2SO4. And it got the proton from the water, so that would make the water now OH minus. So if you were to draw the tie lines, if that helps. And then it can also, so at this point it was a base, it accepted a proton and became H2SO4. It can also be an acid. So if it's going to be an acid, it'll be in water, and then it will donate its proton and become sulfate. And then the water will be the one that accepts that proton and become hydronium. So it's not just water, but other things can be amphoteric, which means they can be an acid or a base. So we know that water will ionize on its own, self-ionize, auto-ionize, dissolve in itself. It's only really to a very small extent, about 1 or 2 molecules per 555 million will do this. So because it doesn't do it to a large extent, you would expect the equilibrium then to lie to the left. We're going to find most water intact and not very much of it broken up, right? So let me just think about the order I'm going to teach this to you. So let me go back here. So if we were to, let's even write water this way, where it's 2 waters together, and then, one of them acts as, that one would have acted as a base, this one acts as an acid. If I were to write the KQ expression here, remember it's products over reactants, I would take that hydronium ion and hydroxide ion concentration, multiplied together over the reactants. But these are liquid, and remember, liquid water, liquids and solids have a constant concentration or molarity. So KQ of water is hydronium times hydroxide. That KQ, we can also write it as just the hydrogen ion. We can interchange that with hydronium. And one last thing, because we're talking about water and this is special for just water, we change this now to W. So it's really just the KQ of water, but we do call it KW. So the value of the KW is 1.0 times 10 to the negative 14th. So really small means the equilibrium lies to the left, which means the water tends to be intact. pure water, then the hydronium ion, sorry, all these H's, each of these would be equal. So they would both be times 10 to the -7th molarity. And maybe that's got you thinking about what you've heard about pH of 7 is neutral, and that is exactly where we're going with this eventually. So let me just show you before we get to the pH calculations some of the calculations you can do with Kw. So if we know the hydronium or the hydrogen ion, we know Kw always is a constant, so then we could figure out hydroxide and vice versa. So if you know one of these, you know the other. So here's an example. They want us to calculate the hydroxide, so let's just write the expression. It's the hydrogen ion times the hydroxide ion, and this is going to be my X. So I know Kw is always, never changes, 1 times 10 to the -14th at 25 degrees Celsius, but I'm not going to mess with you and give you a different temperature, don't worry. And then the hydrogen ion is 1 times 10 to the -8th times the OH is our X. So if I solve, I get 1 times 10 to the -6 molarity. So my question now is this an acid, base, or neutral? So an acid is going to have more hydronium or hydrogen ions, and a base is going to have more hydroxide. So what you want to do is really compare. This is given to you in the beginning of the question. Which one do you have more of? Do you have more OH or do you have more H? If you look at these values in the concentration, this is the number of moles of OH per liter. This is the number of moles per of hydrogen per liter. So there's more hydroxide. So that means this is going to be a base. So that's how we're starting to look at acids and bases. Both of the ions are present, but which one do you have more of? So that leads us to this slide, just that if they're both equal in like pure water or anything else that happens to be neutral, but if you have more hydronium or hydrogen ions than hydroxide, it's acidic, and then if you have more of the hydroxides, then it's basic. One last type of question. So for this question, where it's similar to the one we just did, but it has a little bit of a twist. They want to know the hydroxide ion. And I'm giving you the molarity of this solution of barium hydroxide, and then I also want to know the hydrogen ion concentration. So the trick here is that if you have something that's not in a 1-to-1 ratio, a base or an acid, you do want to dissociate it. So this would break into 1 barium and 2 hydroxides once it's let into water. So if I made a 1 molar solution, then I'm going to, because there's double the moles, I would have 2 times 10 to the -2 moles per liter of hydroxide ion now, once everything has been dissociated. So now I'm going to use that number and do my Kw calculation. So I know that Kw is hydrogen times hydroxide, and I can sub in 1 times 10 to the -14th, and then hydrogen, and then my hydroxide is 2. So that's the first part. They wanted to know what the hydroxide ion concentration is, and we just did that with dissociating. So when I do the algebra, my hydrogen ion ends up being 5 times 10 to the -13th. So you should be able to tell me whether this is acidic or basic. Look at the difference between the concentrations. Which one do we have more of? We have more of the hydroxide, so we know it is basic.